All right. So this will be part two. I guess we're going to do a third part as well. So right at the end of the second part, okay, we were calculating this surface integral. Surface integral x squared plus y squared ds, where s is the top half of the sphere of radius 1. And I want to do this for two different parameterizations of the sphere. So the first parameterization we took was the one that we talked about earlier, using the the idea of rotating this curve. So this is p equal to 1 minus t squared on this pt plane for 0 less than or equal to t less than or equal to 1. And you get this quarter circle. I'm going to rotate that around the z-axis, right? And that'll give me the top half of this sphere of radius 1, right? So that was one parameterization. Let's try another one. Remember, we can represent the sphere using spherical coordinates. All right, so let's say r of theta phi, where x is equal to cosine theta sine of phi, rho equal to 1, sine theta sine phi, rho equal to 1, cosine phi, right, with rho equal to 1. So this is for 0 less than or equal to theta less than or equal to 2 pi. And since we're just doing the top half of the sphere, phi goes from 0 to pi over 2. Now, we're not doing a calculation in spherical coordinates. We're simply representing the sphere natively in these two coordinates, theta and phi. There's not going to be any conversion. Don't be confused about that. There's not going to be any conversion from x, y, z to rho theta phi. There's not going to be any conversion like that. That's when you had the, triple integral dv, turns into this triple integral with the rho squared sine phi, d rho d theta d phi, these conversions into spherical coordinates. That's not going to happen here. That's not going to happen here. We're just natively working in theta and phi. No conversions happening. Okay. So remember the ingredients that are needed for calculating the surface integral. Scalar surface integral. Not into the vector surface integral just yet. Okay, we need f of r of, so we're doing theta and phi now. Theta and phi, r of theta cross r of phi. Not r of theta, sorry, r, partial derivative of r with respect to theta, partial derivative of r with respect to phi. Okay, so, well, f of x, y, z was what? So we got to get all those ingredients first. Right, we're calculating the surface integral over s, x squared plus y squared ds. Right, so f x, y, z was x squared plus y squared. So f of r of theta of phi is equal to, so x is cosine squared theta sine squared phi plus sine squared theta sine squared phi. So I have cosine squared theta plus sine squared theta times this constant sine, common factor sine squared phi. So I just get these adding up to 1 and leaving that common factor sine squared phi. So f of r of theta, f of r of theta phi is just sine squared phi. Okay? All right. Now we need partial derivatives. partial derivative of r with respect to theta was equal to, so remember phi is a constant here, minus sine of theta sine of phi, cosine theta sine phi. No thetas here, so it's just 0. No, sorry, not r of theta. R, partial derivative of r with respect to theta. Partial derivative of r with respect to phi, okay, is cosine theta cosine phi. Sine theta cosine phi minus sine phi. Now we got to do that cross product, and the cross product can be in either order because you're just going to take the length at the end, and changing the cross product around doesn't change the length, it just negates it. So we've got I sine theta sine phi minus sine theta sine phi cosine theta cosine phi j cosine theta sine phi sine theta cosine phi 0 minus sine phi. So that cross product is, now there's going to be a lot of simplifications here. So minus sine squared phi cosine theta. So this minus that, 0. And then in the j coordinate, it's going to be 0 minus 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 that. So that's sine squared theta sine phi, or sorry, sine theta sine squared phi. Sine theta sine squared phi. And then in the k coordinate, it's going to be minus sine squared theta sine phi cosine phi. Minus cosine squared theta sine phi cosine phi. Equals minus cosine theta sine squared phi sine theta sine squared phi. So now I have sine squared theta, cosine squared theta, and a common factor, sine phi cosine phi, subtracted both times. So the sine squared and cosine squared add up and leave the common factor. Minus sine phi cosine phi. That's the cross product. So the length of the cross product, r theta, r phi, is equal to square root of this squared, cosine squared theta, sine to the fourth phi, plus sine squared theta, sine to the fourth phi, sine squared phi, cosine squared phi. More simplifications on the way. Cosine squared plus sine squared, right? And then common factor of sine to the fourth phi gives me just sine to the fourth phi when you add them together. Plus sine squared phi cosine squared phi, factoring out sine squared phi, sine squared phi plus cosine squared phi, which is equal to 1. Square root sine squared phi, which is just the absolute value of sine of phi. But what was the domain for phi? Phi is going between 0 and 90 degrees. So the sine phi is positive, so we don't even need that absolute value. 0 less than or equal to phi, less than or equal to pi over 2. Sine of phi is positive, well, bigger than or equal to 0. Not negative, in other words. So it's just sine phi, right? Because the absolute value of a positive is just itself, or 0, when it's 0. All right. So the surface integral over S of x squared plus y squared ds is double integral over r, f of r of theta phi r theta cross r phi length dA. F of r of theta phi, what was it? It's right here, sine squared phi. R theta cross R phi, sine phi, dA. So that's the double integral over R, sine to the third phi, dA. And what was R? 0 to 2 pi for theta, and then 0 to pi over 2 for phi. Sine to the third phi d theta d phi. No thetas here at all, so it's just 2 pi times integral from 0 to pi over 2 sine to the third phi d phi. Well, what's the antiderivative of that? Basically, you have to do this kind of u substitution thing. You have to rewrite that as 2 pi times integral from 0 to pi over 2 sine squared phi sine phi d phi, 2 pi integral from 0 to pi over 2, 1 minus cosine squared phi sine phi d phi. So now you let u equal u equal cosine. I don't know if you remember this technique from Calc 2. But you let u equal cosine, then du is negative sine phi cosine, or negative sine phi d phi, which is right there. So this becomes 2 pi times integral from 0 to pi over 2 u squared minus 1 rather than u squared minus 1 rather than 1 minus u squared, because you got to negate it. So this is equal to 2 pi times 1/3 u to the third minus u from phi equals 0 to phi equals pi over 2. Switch it back to phi. And obviously this is, very much the same thing. 1/3 cosine to the third phi minus cosine phi from 0 to pi over 2, almost done, 2 pi. So now this is 0 minus 0, and then here it's 1/3 minus 1. Minus 2/3 negated 4/3 pi. Same answer as before. 4/3 pi here. And then using that other parameterization, we still had 4/3 pi. This one worked out way easier, right? I mean, the integral in the end was just this. Okay, by the way, notice that I did not do any conversion, especially in this problem. I didn't do any conversion from x, y, z to rho theta phi. There's no rho there, actually. Rho is always 1. I did no conversion like that. So in the end, after I set up the whole shebang there, I'm left with this, right? Double integral, surface integral, x squared plus y squared ds is the double integral over r, f of r theta phi times r partial derivative with respect to theta cross partial derivative with respect to phi, length times dA gives me this double integral. And this double integral is in terms of theta and phi to begin with. No conversion, no conversion factors. You just solve. Think of theta and phi as x and y. There's actually no theta in there, but there's just the phi. That's fine. In general, there'd be both. So it's just instead of x and y, I got theta and phi, just two different variables. No conversion to different types of coordinate systems. Okay, not that you never would, do a conversion like that. I mean, if it were appropriate to do so, you might actually do so at some point. Let's see. Do I have another example? That might. Yeah. Here's an example. Let's calculate the surface area of the paraboloid. So calculate the surface area of the paraboloid z equal to x squared plus y squared for 0 less than or equal to z less than or equal to 1. Right? So we've got the paraboloid from z equals 0 to 1. Alright, so it's this paraboloid shape. And what is the image of that guy in the xy plane when you project it straight down? Well, when z is equal to 1, and x is equal to 0, y is equal to 1. So that's y equal to 1 there. And then when y is equal to 0 and z is equal to 1, that's these points right there, x is equal to 1. So I'm going to use that standard or trivial parameterization. Rxy is x is x, y is y, z is the function, x squared plus y squared, over domain R, and that's the circle of radius 1 in the xy plane. One. That's the circle of radius 1 in the xy plane. Okay, so remember, surface area is equal to the surface integral of 1 ds over s, which is the double integral over r. This is rx cross ry dA. So all I need to know is what rx cross ry is, and that's pretty easy to calculate, a lot easier than that other example there. So partial derivative of r with respect to x is 1, 0, 2x. Partial derivative of r with respect to y, 0, 1, 2y. So rx cross ry is I, j, k, 1, 0, 2x, 0, 1, 2y. So this is equal to minus 2x minus 2y, 1. So the length of rx cross ry is equal to 4x squared plus 4y squared plus 1. Right, so this is equal to the double integral over r, which was the unit circle, right, of square root 4x squared plus 4y squared plus 1 dA. Okay, so this is an integral with x and y. Now how am I going to calculate it? I either have to integrate it iterate it in terms of x and y, or Now I could decide, well, I'm going to do a conversion. Now let's convert to polar. Everything was set up. Everything was set up in terms of variables x and y. So what I'm left with here is a integral in terms of x and y. In the previous example, right, I did the setup in terms of theta and phi. And what I'm left with is an integral in terms of theta and phi. In the first example, I did my setup in terms of t and theta. And I'm left with an integral in terms of t and theta. Theta doesn't appear in there, but it's, it could in general. But it's an integral in terms of t and theta. I didn't do any conversions. Okay, I just started with t and theta, and I ended with t and theta. Now, in this problem here, I started with x and y. I'm ending with x and y, but I don't like x and y here. I want to do it in terms of polar. So the unit disk is 0 less than or equal to r less than or equal to 1, 0 less than or equal to theta less than or equal to 2 pi, right? So this is equal to the double integral from 0 to 1, 0 to 2 pi, 4r squared plus 1 r dr d theta. Right, so now this is, we have to let u equal 4r squared plus 1. So du over 8r is equal to dr. I need to do a u substitution here. So I got 1/8, the integral from 0 to 2 pi, integral from 0 to 1, u to the 1/2, r, and then r cancels. So that's du d theta. Oh, and this is r equals 0 to r equals 1. Okay, so this is equal to 1/8, integral from 0 to 2 pi. So that's 2/3 u to the 3/2 from r equals 0 to r equals 1, and then d theta. So this is equal to 1/12, integral from 0 to 2 pi, 4r squared plus 1 from r equals 0 to r equals 1, d theta. So we have 1/12 integral from 0 to 2 pi. So at 1, we get 5 to the 3/2. I missed the 3/2. We got 5 to the 3/2, and at 0 you just get 1 d theta. And that's just a constant, right? It's all just a constant. So that's equal to 2 pi times that constant. So this becomes a 6. So this is equal to 5 to the 3/2 minus 1 times pi over 6. So that is the surface area of that paraboloid. So it's an ugly number, but there it is. Okay, so this surface integral allows you to do a surface area calculation, just like the line integral allows you to do an arc length calculation. So this is the end of the lecture on section 6.6 part 2. Next time in part 3, and we won't get to that tomorrow, but next time, we will do the vector surface integral. But this is enough for now. It's quite a bit of material. Okay, so I'll stop the lecture there.